In the last lesson, we ended the story here in the Dark Ages, where hydrogen and helium were present, but no stars had formed yet. Well, that will change. Hydrogen atoms can join to form hydrogen molecules, and this is hydrogen gas, and giant clouds of these hydrogen molecules were compressed under the force of gravity. And as gravity condensed these clouds, the temperature and pressure increased and increased, and at a certain point the pressures and temperatures are so high that hydrogen nuclei will fuse into helium nuclei, and this releases energy. In a sense, a little bit of mass is being turned into energy, and this is what makes stars shine. Now, we've also learned that the light from stars is basically white light. All the colors are present, but stars have cooler atmospheres, so some of the light will be absorbed by the atoms in the atmosphere, and that will show up as absorption lines in the spectrum of starlight. Again, just to review, the process of nuclear fusion is the process where hydrogen nuclei are fused to form helium and energy is produced. So a star is a fusion reactor. The gravity is what keeps the temperatures and pressures high enough here for the fusion reaction to occur. And this makes stars radiate heat and light. Back to the absorption spectrum, the reason why you'll get absorption lines in starlight is because the atoms in the cooler atmosphere, those atoms, remember, have these energy levels. Those atoms are going to be absorbing certain colors. If the color of light has the energy needed to bump an electron up to a higher energy level, then that color of light will be absorbed, and we'll see that as dark lines in the light from the star. And depending on the pattern of these lines, then we can determine which atoms are present in the atmosphere. You'll recall that different atoms have different arrangements of energy levels. That makes different jumps possible, and so you'll get different spectra. And this is the emission spectra, which would be the same as the absorption spectrum in terms of the pattern of the lines. Notice atom Z has a different arrangement of the energy levels, and so you'll get the emission of different colors of light. Now, after the formation of the first stars, then, we're going to get the formation of the first galaxies. Galaxies are just giant collections of stars, and there are all kinds of different shapes of galaxies. We're familiar with spiral galaxies because the Milky Way is a spiral galaxy. But there are lots of galaxies that have an elliptical shape, and galaxies can collide, and the gravitational disturbance can give rise to all kinds of messed up configurations. A spiral galaxy, if seen from sort of above, in a sense, there is no real up in space, but from this angle you'll see the core of the galaxy and then these spiral arms. So a galaxy may have a couple 100 billion stars. If you see it edge on, then the galaxy looks something like this. And if this were our galaxy, the sun would be out here in the kind of the the suburbs. If the core of the galaxy would be the inner city, the sun would be out here in the suburbs. Now, galaxies being composed of lots of stars, the light from galaxies is also going to have absorption lines. And this, of course, will play a significant role in Hubble's discovery about the expansion of the universe. Down here we have a helpful sort of analogy to understand the dimensions of our universe. If our universe were the size of a classroom, then galaxies would be the size of little dust particles, a little speck of dust in the room. And recall from the microwave background radiation picture, these clumps, the brighter regions, are clumps of denser matter, and these will be future galaxies. So the distribution of galaxies today in our universe was sort of set in motion by these early little differences in density of matter in the earliest phase of the universe. It's now time to tell the story of one of the greatest astronomical discoveries in science, and it was made by Hubble right here in Southern California. In the early 1900s, it wasn't clear what these little fuzzy spots in the night sky were. As far as anybody knew, they were just weird fuzzy things in our, in a sense, galaxy. And it could well be that everything that we were seeing was just in our galaxy, and the entire universe was just our galaxy, the Milky Way galaxy. Well, Hubble, using this telescope on Mount Wilson, directed his telescope to these nebulae, and he was in search of stars that change their brightness. They're called Cepheid variable stars, and astronomers had worked out that if you can find such a star and you can measure how long it takes it to change its brightness, you can then figure out how intrinsically bright it is. And then you compare that to how bright it appears, and you can work out how far away the star is. Now, this is the Andromeda Galaxy as pictured from a modern telescope, but this is the actual Cepheid variable star that Hubble identified. And you can see over the course of days it gets brighter. And Hubble identified one of these stars in the Andromeda Nebula. And here's the actual plate of Hubble's, and he has indicated between those two lines there's a little star there. That's a variable star, VAR for variable. And so he was able to work out the distance to this nebula, and it was outside the Milky Way galaxy, which meant that the Andromeda Galaxy was, or the Andromeda Nebula was actually a galaxy all its own. So all the stars that we see in the night sky are in our Milky Way galaxy. We're looking at the core of the Milky Way galaxy here. This picture was taken with a 20-second exposure off the California coast north of Santa Barbara. The galaxies that we see in the night sky appear as just these fuzzy patches, but they themselves are collections of hundreds of billions of stars far away from our own galaxy, about 2.5 million light years for the Andromeda Galaxy. Today, with the Hubble telescope, with exposures of 11.3 days, the Hubble telescope has revealed thousands and thousands and thousands of galaxies just in a small little patch of space. And so there are hundreds of billions of galaxies in the entire universe. All of the little spots of light here are galaxies, with the exception of these stars, which would be local stars in our Milky Way galaxy. Not only did Hubble discover that there were galaxies separate from our own, so there were multiple galaxies, but he also gathered evidence that they were moving away from our galaxy, and that the farther away the galaxy was, the faster its velocity away from us. Here we see that relationship in graphical form. This would be the distance to the galaxy on the x-axis, the velocity on the y-axis, and there was a relationship. Galaxies that were farther away had higher velocities. Galaxies that were closer had lower velocities, but all the velocities were away from our galaxy. Now, why would galaxies be moving away from each other? This led to the idea that space was expanding between the galaxies. So this is the idea of the expansion of space carrying galaxies away from each other. Well, if space is expanding now, then it must have been smaller in the past and smaller in the past, and you logically get back to a point where the universe began. And this idea came to be known as the Big Bang Theory. Now, Hubble didn't just, discover that there were other galaxies and that they were moving away. He was able, in order to do these calculations, he was able to work out how fast the galaxies were moving away. So again, galaxies that were closer to our galaxy were moving away, but at a lower speed, a lower velocity than galaxies farther away. But how do you measure the velocity of a galaxy? Well, here's how we did it. We know that galaxies are composed of stars, and each of those stars will be producing a continuous spectrum of light. But the light must pass through the atmospheres of the stars and also all the interstellar gas and dust before reaching Earth. So the light from galaxies like the Andromeda Galaxy will have absorption lines. Now we know if a light source is moving away from us, the light will be redshifted. If our eye were here and the light source is moving to the right, then the light coming from that object will be stretched and so be redshifted. If the light source is moving towards us, so this eye over here, the light will be blue shifted. So when we say that a distant galaxy's light is redshifted, and that's what Hubble discovered, astronomers are referring to the shift in the absorption lines of known elements. That's how Hubble was able to determine how much of a redshift. So we drew the picture like this. Here we have the expanding universe, and we have galaxies that are moving away from each other because of the expansion of space in between. And what Hubble measured was the galaxy farther away had a greater redshift. The absorption lines from the light from the galaxy were shifted towards the red. Here we see a better picture of that. We have Galaxy A and Galaxy B over here. Now up here we have laboratory reference, so maybe these are absorption lines from the sun. We see that Galaxy A has a redshift of this magnitude. So it shifted this magnitude here. The absorption lines were sort of in the green and the yellow. Now they're in the yellow and over here in the orange. Well, that's a certain shift associated with the velocity. So Galaxy A is moving away at a certain velocity. Well, if we compare it to Galaxy B, that's down here. Here again is the laboratory reference, absorption lines from the sun, for example, and notice the shift is larger. And this means that the light from Galaxy B, traveling a greater distance, was stretched more by the expansion of the universe, of space in between. And as a consequence, the Galaxy B is receding from Earth at a faster velocity. So the larger redshift means a greater velocity away from us. In this pattern then, where the nearby galaxies and the more distant galaxies have different speeds, is nicely explained by the idea of an expanding universe. Well, if the universe is expanding now, then at some point in the past there was a Big Bang. So today when we use telescopes, we're peering back in time. And in fact, some of the new telescopes are going to be like the James Webb Space Telescope, are going to be collecting light from the earliest periods of time in the universe. As we look out into the night sky, we're looking back in time. Of course, the fact that our universe has billions of galaxies, each with hundreds of billions of stars, does raise the possibility, could there be some other kind of intelligent, lifelike creatures in the universe? And that's exciting to contemplate, but scientists are well on their way to trying to discover habitable planets, or planets that are in the habitable zone that might support some kind of lifelike organisms.